We have shown that this is possible along the way. We have paralyzed people who can control their using the brain computer interfaces, their wheelchair. As people learn to use a brain control device, their brain is changing the way it is generating patterns of activity, the intentions that you want that device to perform for you. But the reality is that any kind of technology that we have today requires humans to adapt to the technology. A brain-computer interface, this is a revolution, may eventually help us achieve the dream of having machines adapting to us in the personal way that we want.
Following is a conversation with Dell Millan. Josh is a professor at Department of Electrical and Computer Engineering at the University of Texas, Austin. Also a professor in the Dell Medical School, Department of Neurology. This is Sanjeev Ranjan podcast, and here is Dell Millan. Hi, Josh. Welcome to my podcast.
Hello, nice to meet you.
Likewise. So, yeah, could you please tell us something about your professional background, your professional journey in the field of neuroscience, how it started, what motivated you to start this journey and keep on continuing on this journey? So, what excites you most in your this journey in the field of neuroscience?
So it is a long journey with plenty of bumps, but this is what makes the journey interesting, I believe. So I am not a neuroscientist as a background.
Mhm.
Formally, I did my all my education was in computer science and in artificial intelligence. And as a matter of fact, I started to work for my PhD and then for my continuation, my professional life in robot learning. So robot learning at those days was not very well established because there were very few robots. And the fact that it was possible for robots to learn from their own experience, it was not yet very well established. Today it is. We have autonomous robots, autonomous car everywhere. So this is where I started. And then at a certain moment, I started to wonder, well, which would be the most useful kind of robots that could help us humans? And I came to the conclusion that what we needed most was the possibility to have robots that could interact with humans so that human and robots can do things that humans alone could not do or could be done better. And in this thought process of how we could humans interact with robots and how robots could interact with us in order to help us, I came through the case of a couple of people who were tetraplegic, meaning completely paralyzed from the neck down. And they couldn't barely speak. They could barely communicate an intention. And then I thought, well, this is the most useful example and case study for human-robot interaction, because these persons are still cognitive aware. Their brain was okay. They could go through all the cognitive processes that any person who doesn't suffer from any kind of motor disability can go through, but they cannot implement those cognitive decisions because they cannot control their body. So why not to have a robot that will somehow infer which is the intention of the person and execute that intention on their behalf? And this is why I started to look at the field of brain-computer interfaces or brain-machine interfaces. They are called both ways: brain-computer interfaces, BCIs, or brain-machine interfaces, BMIs. Because in any case, what we want is to have an interface between the brain, from which we will be recording brain signals in order to infer which is the intention of the person or the cognitive state of the person, and to transfer that to a computer or a machine, a robot in this case, that will perform that intention, will materialize that intention. So at that moment, I started to learn first about the brain. So this was where I started to enter into the field of neuroscience. And I started to learn about how to process brain signals. And so this brought me towards the field of biomedical engineering in order to understand how to process these information. And then I kept all my artificial intelligence, machine learning background, because at the end of the day, you have data in, so the brain signals that you are recording, and you want to get decisions out, which is the intention of the person as encoded in the brain signals that we are recording. Well, I thought that this would take me to build a brain control robot a couple of years. Of course, I was young at that time. I was very naive at that time. This was more than 20 years ago. And well, I am still here trying to solve that problem. But we have shown that this is possible along the way. We have paralyzed people who can control their using the brain computer interfaces, their wheelchair. We have people who have been controlling hand or prosthesis, neuroprosthesis, in order to regain control of their hand that is paralyzed, walking machines so that they can step and walk again when they are paralyzed. So we have many examples of those brain control robots, even if I am not yet satisfied with the performance of those brain control robots. This is what keeps me busy.
Okay. Sounds like a very inspiring journey, because it's also one of my favorite area, the neuroscience together with technology. So leveraging technology to help research in neuroscience. And yeah, and it has, as you said, that it has quite some impact on the people. Means it can literally change life of a lot of people who need it. So could you please tell us something about how about the development in neuroscience from, let's say, from the last 50 years till now? Means how it has it been quite rapid development, or it has been quite steady development over last 50 years? Means how how it has happened so far, and how it's going to be in the future? How you see that with the new technology coming like AI? Do you see it getting even more fast development in the future, or it will be static? So how everything will fold out in the future also? So past and the future.
Okay, so well, definitely the field of neuroscience is witnessing a huge progress over the last 50 years. Why? Because the brain is one of the less known and understood organs in the human body and in the mammals in general. Why so? Because of the complexity of the brain. We have so many neurons, and neurons are not only the key element of the brain, it is the connections that neurons have among themselves. And then if on average one neuron has, I don't remember the exact numbers, but tens of connections, synapses with other neurons, then this number becomes huge. So we don't have the means to understand these how the information is generated in the brain, and it is somehow processed in the brain and pass over from one area to the next, so as to allow animals and humans to make decisions and to implement those decisions. This is where the field of artificial intelligence is revolutionizing the field, because now we have the means to process huge amounts of information and to understand which are the patterns that are encoded into those, at the first glance, random patterns of activity of our neurons in a given brain area, and even more so when we scale up to the whole brain. But in order for artificial intelligence to be able to help and to provide hints of which are the processes that the brain is implementing in order to somehow infer information from first inputs that can be our senses, but can also be triggered by internal processes, we need to measure the activity of neurons. And this is the other kind of technological revolution that is happening over these last tens of years. Because at the very beginning, we could only record one neuron if we were lucky. Now we can record thousands, or at least hundreds of neurons in parallel at the same time. And we can have technology like functional magnetic resonance imaging, where we need to have a big, huge scan that will create a magnetic field, and we will be able to observe the areas of the brain that are turned on and off as people inside the scan go through some processes, mental processes, that can be as simple as moving your finger, or as complex as solve this problem, as complex as that problem can be. So the fact that we have this combination of new technology that will allow us to measure in real time the functioning of the brain with artificial intelligence that will be capable to find patterns in that huge amount of information is with what it is pushing the field of neuroscience. And I would like to add a little thing. So when I started in the field of brain-computer interfaces, of course, I had to learn about neuroscience, the organization of the brain, the principles of brain function, etc. And brain-computer interface was not considered a serious thing by neuroscientists. This was a kind of toy. And then what we are observing lately is that the techniques that have been developed in the field of brain-computer interfaces have permeated the whole field of neuroscience. Why I am saying so? Because originally, because of the technology and the techniques that neuroscientists were using, they could only answer questions that require many decisions, so that they could average one and a second and a third and a tenth and hundreds of responses, so that they could understand, oh, this is the average response of the brain to that situation. Whereas what we know is that cognition is not you trying to answer the same question 1,000 times to come up with the right solution. It is that you need to answer the question here and now. You don't have a second opportunity. This is cognition. When you need to go through in real time through this process. And this is what essentially a brain-computer interface does. Show me the data of, the neural activity, and I will tell you which is the state of the person here now, because we need to take a decision here now. So I am very proud that as a field, brain-computer interface researchers have
Yeah.
field of neuroscience.
Yeah. And could you please tell us about brain computer interface itself, because this could be a term very new for some of our audiences. So it would be nice to have a small description about the
Yeah,
BCI.
with pleasure. So a brain-computer interface is a system that will record brain signals in real time. This can be through an implant, so you will need to put electrodes inside the brain of the person, or it can be through non-invasive techniques. For example, the electroencephalogram, where the electrodes will be simply in touch with your scalp. Or it can be also a functional magnetic resonance imaging, this scanner where the person enters and it will be taking pictures of the activity of the brain as the person is going through some task. Now that we have this data collected in real time, we need to apply machine learning techniques in order to infer which is the intention of the person. And what do I mean by intention? Intention can be, for a paralyzed person, I want to move my paralyzed right hand. Of course, I cannot move my hand, but I can still generate the order in my brain, in particular in the motor cortex, that is on this part of our brain, so that this activity will represent the intention of moving my hand. And now the machine learning will infer whether the person wants or not to move the right hand and how eventually the person wants to move it, or whether he wants to move the left hand instead. And the next stage will be, okay, now we have inferred that the person wants to close the hand, say, and now the brain-machine interface or brain-computer interface will give the order, say, to a hand exoskeleton, so a device that will be around the paralyzed hand, motorized, that will close the hand as the intention of the person, or will open it if the person wants to open the hand. And finally, and this is critical, a brain-computer interface requires feedback in the same way that you and me do whenever we are using our body. You cannot see the position of your hand or your feet, but you know which is the state of your hand and your feet. Meaning, you want to close your hand, even if you cannot see it, you know that your hand is closed, or if it is not closed. And this is because we have the sense of proprioception, the sense of where our body is in a space. Why this is important? Because if we don't know which is the state of our body, we cannot accomplish any meaningful action. Because I will be lost. I don't know whether, for example, I am reaching for the key in my computer to press in order to write the word I want to write. So the fact that in a brain-computer interface, the intention of the person is transformed into an action that provides feedback to the person. In the case of the hand exoskeleton, I will observe my hand closing. I will somehow feel a little bit that my hand is closing. This will allow the person, this feedback, to learn how to modulate their brain signals in order to convey their intentions better and better to the machine. Because at the end of the day, a brain-computer interface is a skill, as any other skill that we learn.
Yeah, yeah. And that means that for this close feedback loop, BCI has to be used two times. Once from sending signal from mind to any body parts to control it, and then from the body part back to the mind, that okay, the hand is moving as expected or not, so that person can train. So BCI is converting is the interface at the in the both directions.
Yes, definitely. And sometimes we don't require any actual movement of our body. Because, for example, I can imagine, so one big, how to say, a fundamental function that we all have as humans is communication. This is what allows us to create binding across people, because we can communicate. Well, but people who are unfortunately paralyzed, they can't barely communicate. So could, or they suffer serious lesions in their brain. So how can we restore communication? A possibility is to use a brain-computer interface so as to allow people to select letters in the virtual keyboard rather than the physical keyboard that we all have in our computer, so that they can select letters, compose words, sentences, send those sentences to the other end, and establish this communication. How can we control the selection of letters and the composition of words? Well, in the same way that when you are typing, you are using your hands in order to type on the keyboard, you can use the brain computer interface to say, okay, now select the right side of my keyboard, because I will be imagining I am using my right hand, rather than selecting the left side of my keyboard because I am imagining using my left hand. So that now you can navigate. Or you can say, well, I have a cursor that I will be controlling as when you are using your mouse, so that I am moving the mouse in order to reach for the letter I want to select. But this is a movement of your arm, isn't it? That you are doing in order to control your mouse. You can mentally replicate the same process, movements that are not transformed into actual movements of your body, but rather final actions accomplished by your body.
Yeah, means uh, very interesting use case. Means the I mean, it feels like we we only need our brain in our body, and if we don't have anything, that is always replaceable. Not now, but maybe in the future, if somebody have ability to learn new skill, and then that person will have very less will it will be very less likely for that person to feel disabled, because using
Yeah,
his mind he can do all the work, like you mentioned, like you explained, and so he can feel like a complete human rather than a disabled, and that
yeah,
makes this technology
yeah,
very
yeah, yeah,
great,
yeah.
in my perspective.
Yeah, because one of the especially in the case of people with severe motor disabilities, the purpose of a brain-computer interface is to restore or to regain function, so that the effects of or the impact of these motor disabilities are less severe. Now, there is a long way before a brain-computer interface can operate these alternative devices, assistive devices, as efficiently as people without any kind of motor disabilities. We use our body, because we have been learning to use our body since we were born. And remember that babies take a long time, years, to learn to control their bodies efficiently. It is not a
Yeah,
question of a couple of days, it is years.
yeah,
So
yeah, yeah,
we need
yeah,
to
yeah,
train. Mm.
yeah. Means so the crux of the discussion which we just had is that people who are good in learning new skills, they are going to have advantage in this case also. So they are going to have advantage, of course. With the new technology, AI is coming, a lot of jobs will be replaced, and the people who are able to learn new things quickly, they will have an advantage there. In the same way, the same kind of people who are able to learn new skills quickly, they are going to have advantage in this kind of BCI technology also, because
Well, I would like
normal.
to I would like to comment here because so in the way it is said, and it is true, because learning is a question of attention. You need to put a lot of attention on the task that you are trying to learn to solve. But then we know that let's use the case of sports because it is very visual, not because it is particularly significant. It is because it explains very well what happens. In order for a person to excel in sports, of course, they need to practice. But we all know that certain persons are born with some innate abilities that others don't have. And you can practice if you don't have those innate abilities. And in particular, let's take the case of basketball. Well, if you are like me, I am short, but I will never excel in basketball, no matter how far I go in my training.
Yeah, you mentioned very interesting point, and that makes me wonder, what if BCI itself can help people to develop their mental faculties, which is comparable to the other person who born with those innate capabilities like attention. Can BCI
Yeah.
help people who have less attention to be more attentive, so that they can be on the same level as the other set of people or group of people who are born with good attention capability?
In principle, yes, because we could have a BCI that is monitoring your degree of attention. And then it can warn you whenever your attentional attention diminishes. Now, is this sufficient? Yes and no, because what it is good is that we will have an objective way to know when we are really attending the task or when we believe that we are attending, but actually we are not. And maybe you yourself, you practice meditation. And this is a key. At the very beginning, the key question is to know when you are in the good meditative state or when you are not. And you may believe that you are when you are not. So if you have a good way to objectivize when you are and when you are not, well, you will eventually go faster in acquiring this sense of when you are in the flow and when you are in the good state. Now, once you are in the good state, this doesn't mean that you have solved the whole problem. Now, in a given sense, the whole problem starts because now you need to learn how to do it. And this is a question of practice, and practice cannot be replaced. Technology cannot replace
Yeah,
practice. It
yeah,
can help to maximize the outcomes of practice, but cannot replace practice.
and and can it be like again a closed feedback loop? A person gain a little bit of attention using BCI, for example, and then he try to learn skill to control his hands, artificial hands, and then and then if he's able to control it in a good way, then he could be sure that I am not just believing that my attention is good, but it's actually good. So there could
Well,
be a feedback loop there also, and
of course, of
then
course.
he know that he's not fooling himself, and he's on the right path to gain
This is
attention.
what I meant, but you have expressed that very nicely. This is what I meant when I say we will have an objective way too, because then you will see the effects. It is not simply a belief, an impression, is that you see that all of the sudden it is you have better control or you are or whatever you are trying to do through the brain computer interface is more efficient. This is important. But I also want to bring up another element to this learning process. So we have technology that is very powerful, but technology, no matter how complex it is, has always limitations. So we can sense, we can measure brain activity, but we need to remember that the cortex, where most of our cognitive functions and motor control decisions are initiated, has a very strange shape. It is not a flat surface. Our cortex is not a flat ball. Our cortex is made of a lot of meanders. There are valleys, and so deep valleys and mountains. So it is very convoluted. Okay. Now, when you are measuring the brain, say with an implant, the implant will most probably get into the how to call it, the hills of our cortex, but it will be very difficult to reach the deep valleys. The same when you are measuring from the external EEG, these external electrodes. It will be easier to measure the part of the cortex that is closer to the electrodes than those that are deep in the valleys that are farther away. This means that we will not have a perfect image of how our brain is working. And if for whatever reason, the sources of the intent that you want to convey through the brain-computer interface are in deep valleys, well, it will be more difficult to sense and to decode. And there, it is not your fault. You can be as attentive as you want, but the information, the signals are lower quality than for another person. This is why I was saying, well, there are people who have some innate capabilities. In these cases, by chance, whenever I imagine moving my hand, these sources are on the hills. It is easy to sense them and to decode. Whereas for another person, it will be in the valleys, so it will be more difficult. Learning means you will be able, ideally, to move these sources from the valleys to the hill.
Wow. It does not sound like that straightforward task.
Well, but this is all what we do all the time. This is learning. This is practice. Whenever we learn something, and we are learning something new every single day, this means that our brain has to encode that piece of information, because otherwise we are not learning. We get it and we forget it, isn't it? So if you learn it, your brain has to encode it. And if your brain is encoding new information, this means that your brain is changing the way it is working in order to accommodate that new piece of information. And this is what we want people to do through the training of the use of a brain-computer interface, that they are learning new pieces of information, that they are changing the way their brain activity is generated. And this is plasticity, brain plasticity.
Yeah.
And now let me make a jump, because this is fundamentally my journey in neuroscience. If the use of a brain-computer interface enables plasticity, and we have a lot of evidence that as people learn to use a brain control device, their brain is changing the way it is generating patterns of activity, the intentions that you want that device to perform for you. If this is true, then this means that we can use brain-computer interfaces not only as an assistive device, the wheelchair that will allow you to move from one place to another, the virtual keyboard that will allow you to compose messages. We can also use brain-computer interfaces for rehabilitation, What is rehabilitation? Rehabilitation is the process of, after a lesion to our central nervous system, going through a therapy that will allow you to recover the function that were lost because of the accident that you had. And this can only happen because the brain will reorganize so as to transfer the function that was encoded in the part of the center of the brain, in this case, that has been damaged, to another part nearby that is healthy, so that this function will be available for your brain to express it via your body. And this is rehabilitation. And this is how brain-computer interfaces are being used to accelerate, to improve the degree of functional recovery because of the plasticity. And this is what excites me more. This is what I am devoting most of my time. How to induce this plasticity in order to recover functions that have been lost. But now we are recovering function because your body itself will be able to execute them again. So you will recover the movement of your hand that was paralyzed. Not yet as well as before, but definitely better than after the paralysis.
Yeah, and does it also help to improve? So it helps with recovery, which you just explained, and that's for disabled people or people who need rehabilitation. How about normal people? Like, can it help them in improving their intelligence, their wisdom, for example?
Maybe. I don't think that this is yet the case, or it will be the case in the next 10 years. But what we can envision for people who don't suffer from any physical disability. So first point, brain-computer interfaces are great, but we need to remember that their performance is still very low. People who are using hand exoskeletons, they will never be using the hand exoskeleton as a normal hand, okay? They are slow, they are not as precise. So there is a long way still to go. This means that you and me, if we don't have any paralysis, we may dream of having a third arm. That would be great to have a third arm, isn't it? This will allow you to do things that you cannot do today. Yet, the function will be so limited that actually you will not never use it because it is so slow, so low performance that you will never use it. Nevertheless, we are interacting all the day long and more with intelligent systems. And a computer is an intelligent system. In a computer, you want to go from process A to process B. Whenever you are interacting with your car, you are performing actions and you are anticipating to do other actions as a function of the traffic conditions. Now we have, let's use the case of car driving. We have autonomous cars, isn't it, that can do many things by themselves because they are equipped with sensing cameras, lidars, so not infrared, ultrasounds that are sensing the position, the speed of other objects around the car, and can decide how to drive safely. Well, in the case of a driver, you can do that too, but the car, because it has a lot of intelligence now, will be replacing some of your actions by other actions that you don't know what they are. Imagine now that we are using a brain-computer interface that is capable to anticipate some actions that you will be doing, like braking, like changing lanes, like accelerating. Well, if we have this piece of information, say half a second before you do it, now we could send this cognitive state of the driver to our intelligent car so that it will be able to help us drive better using our intentions, not what the car believes it should be the best way. I want to use this example that we have demonstrated it is possible to say that brain-computer interfaces can help in enhancing the quality of the interactions that we have so that we can do things and machines can help us achieve tasks faster and better because the machines will be adapting to our brain state rather than what happens today, that you need to do things in the way the machine wants you to do. Otherwise, your intentions will never be understood by the machines. So the dream has been always, let's have machines that adapt to humans. But the reality is that any kind of technology that we have today requires humans to adapt to the technology. A brain-computer interface, this is a revolution, may eventually help us achieve the dream of having machines adapting to us in the personal way that we want.
Yeah, means I'm now really looking forward to that future, because when I think of it, then it really feels like that we all are probably going to become enhanced in our capability, more powerful as a being.
Yeah, but we cannot forget that as any new technology, okay? Let's use smartphones that allow us to do things that we couldn't dream of a few years ago. Any new technology will have the risk of creating or enlarging the technological divide of humankind, because there will be people who can afford to have the technology and people who can't afford to have the technology. So in the case of healthcare, uh, this is easier ethically to handle, because eventually if they demonstrate that they are brain-computer interfaces are indeed providing a health service, let me call it like that, that is better than other kind of alternatives, well, any health system will be incorporating them at different speeds, but everybody will eventually have access to that. When it comes to our daily lives, well, this is where the divide will happen. And we need to be aware that we cannot keep using innovations, technological innovations, to accelerate and to enlarge this divide.
Yeah, true. Could it be that in future, because of the recent developments in technology like AI, there could be universal basic income? So let's say after 10 years or 15 years, very few poor people in the world compared to now will be there because of huge wealth generated from AI use, and that can enable us to enforce universal basic income. And by that time, probably in 10, 20 years, these machines, which are very costly, BCI machines, that will become more portable.
Yeah.
Like we in the past, we used to have big telephone we were using at our home, and now we have a small mobile phone at our pocket. In the same way, maybe let's say after 20 years or 15 years from now, we have a device which can a BCI device which is affordable enough for people.
Yeah. Oh, yeah, I believe so, because it is a question of mass production. If the demand is large, cost will go down. and hopefully there will be, as in everything in life, you will have basic cars, middle class cars, and super fancy cars that only a few people can afford to buy, isn't it? So my hope is that we will have, as in any other kind of technology, the same gain or quality. The important thing is that as a car, basic car, it fulfills certain basic functions. Otherwise, it is not a car. You will never buy it because, it is looks like a car, but doesn't function as a car. What I hope is that this technology will allow people with severe disabilities to get back to society, to have a job, to become more independent. Because this is a drama, not only for the person who suffers the physical disability, but for the whole family. Because people require attention 24 hours a day. Someone has to be there constantly with them. So this means that other people in the family will not be able to become independent financially because they need to assist. So this eventually will be a way to free human resources for allowing the whole society to have all of us integrated.
Yeah, that would be great. And and that also means that of course divide is going to increase with the invent of this device, and then it can again decrease also after certain time when there will be more affordable devices, cheaper
Yeah,
affordable devices will be there, and people will have sufficient money as a result of universal basic income in their pocket. Then
yeah,
it
yeah,
will start decreasing at after certain point probably.
yeah,
Yeah, so from BC means I heard in the news that a new technology has been developed in University of Texas Austin, and that uses fMRI to read thoughts of people, and that's a recent breakthrough. To vast extent it is accurate. How accurately it captures people's thoughts, and what could be its result in the future, what could be its best use cases in the future for common people.
Well, this is a colleague of mine here at UT, University of Texas at Austin, who uses the functional magnetic resonance imaging, the scan where people need to go through. Now, what this colleague has shown is that as people are watching films, you are recreating the story of what you are seeing and eventually what you are listening to. And that this information can be extracted from brain signals in order to recreate the dialogue that was going on in the film and describing the scenes, etc., etc. How can this be translated to outside this scan? Well, this is an open question. It is not yet solved. But the important thing is that we know now that this information is in the brain. That as the brain is going through those processes, it is encoding this information and that we can extract that information. So maybe with wearable technology that is not as sophisticated as this brain scan, we will not have access to all the information. But this is where artificial intelligence is innovating. Once we know that this information is there, we can develop algorithms, new AI techniques that will allow us, maybe not with the same level of precision, but with a sufficient level of precision to establish a dialogue. Because this is the main use of that technology, it is not reading thoughts. It is reading thoughts in a context, or reading the language processes that you are consciously elaborating in a context. So that now, again, let's use the case of the paralyzed person who cannot communicate. In a context, we can, through the use of generative AI, large language models, establish this dialogue with a few glimpses of the brain processes that are hints to the kind of communication, the sentences, the speech that the person wants to convey to the other part.
Yeah. And so after reading thoughts, or if we get a context of the thoughts, then I see that probably in future one person can talk to multiple people at the same time, because people generally have mixed thoughts in their mind, multiple things going at the same time, and it could be that and that projects very fascinating future in front of me, like it's going to save so much time. We waste so much time in thinking and then speaking. And if we think, and the next person knows what we are thinking, then we say we are much more efficient. And
Do you believe
secondly,
so? Do you believe so? How many times in our conversation we start saying something because we are speaking out loud?
Mhm.
I don't know yet how to express. And now I will be observing you and realizing that, oh, no, 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 this is not what I want to say. I didn't mean that, because I was speaking too fast. So we need to, what is efficiency? Efficiency is not doing things faster. Efficiency in communication is to sending out the right message and doing so in a way that the receiver will get the message right. Isn't it?
Yeah, you are right. Yeah, you are right.
So, time is not the whole issue. There are situations where time is precious because you need to take a very fast decision, but others where the important thing is to get it right.
Yeah, and probably as you mentioned, the problem and the main thing is to get it right. And probably this can help, machine can help us to get it right, and then reduce time in that way
Oh yeah,
to get our thoughts and our questions or our doubts, and then give us a clear answer with a clear reasoning. So, and then, or give us some options that you can respond in this way, and then we can just choose in our mind, and then whatever we feel is the rightest answer, we can just give. So
yeah.
it enhance the rightness, the correctness of our response.
It can help
So
the convergence so that we both get it right. I want to
yes.
make how to say. I don't like to qualify something that I don't want people to get it wrong. Brain-machine interfaces cannot read thoughts. I say, why not? Before you were saying that it could infer what people were elaborating in language description of images, etc. Is not that a thought? What if not? What is a thought if not that? Well, yes, but the brain-machine interface that these people were using had to be trained. They had to be trained. Remember that. So this means that the brain-machine interface is not about putting you the brain recording system and knowing everything about your thoughts. You need to train your individual brain-machine interface, brain-computer interface, to help the brain-computer interface infer information, the intent, your cognitive state, your language. But it is not reading thoughts as normally it is understood. So I want to reassure people that brain-machine interfaces would not be scanning the whole planet in order to read out individual thoughts so that we have the big brother materialize upon us.
Yeah, thanks for the clarification. And yeah, I mean, so everybody needs to customize their own machine with their thoughts, and the more thoughts they will put in that, the more training data they will provide to that, the more
Yep,
accurate it will read your thoughts next time. So yeah,
yep.
it's like it's a we can compare it with like machine learning models algorithm. Okay, you need to provide data and keep on fine tuning it, and then you are going to get better and better results.
Yep. Exactly. So the big question will be security. How can we preserve the security of this data so that nobody has access to that data but you and your BCI?
And what do you think as a possible solution for that? I was just researching on internet and I came through federated learning. So could that be a solution for the privacy?
Well, yes. The important thing for privacy and security, in the sense that you secure that this data will not go outside with your tag, with your information, is federated learning is one. The use of large language models is another one. Is that we are pulling data from many individuals without knowing which one belongs to whom. This is the way to preserve this privacy, that we are not capable to identify whose data belongs to whom. And now
True.
we can use many techniques. Federated learning is one, but there are
Ah,
others.
yeah. So yeah, with all the new technological developments, there always needs to there is always a need to develop these kind of regulation or security and those kind of things. So to
Yeah.
maintain it. Yeah. So with this, we are already at the end of our conversation. Thank you very much for coming to my podcast. Do you have any last thing to share?
No, I think that we have covered a large amount of topics around brain-computer interfaces, neuroscience, and technology. And well, I am very happy to have spent this time with you all.
Thank you. I'm also quite happy. Thank you. Thank you very much.